Based on calculations, the assessment is correct. For conductor sizing, considering a starting current of 155 amps and a maximum allowable voltage drop of 10%, the formula used to determine conductor size involves the starting current, conductor distance, and the ratio of voltage drop to the maximum allowable voltage drop. For number 2 copper conductors with a distance of 100 feet, the voltage drop is calculated using the formula voltage drop equals starting current times conductor distance divided by the product of the cross-sectional area of the conductor and its ampacity. Substituting the values, voltage drop equals 155 amps times 100 feet divided by the quantity 13.31 square millimeters times 95 amps per square millimeter, which equals 1.23 volts. The ratio of the voltage drop to the maximum allowable voltage drop is 1.23 volts divided by 15.5 volts, which is 10% of 155 volts, resulting in 0.8. Therefore, number 2 copper conductors are sufficient for starting. For overcurrent protection, given a starting current of 155 amps and an overcurrent protection factor of 125%, overcurrent protection devices are sized to protect the motor from damage during starting. The overcurrent protection is calculated as starting current times the overcurrent protection factor. Overcurrent protection equals 155 amps times 1.25, which equals 193.75 amps. Therefore, a 155 amp overcurrent protection device should be considered. Considering full load current and voltage drop, with a full load current of 76 amps and a maximum allowable voltage drop of 5%, the voltage drop is calculated using the same formula. Voltage drop equals full load current times conductor distance divided by the product of the cross-sectional area of the conductor and its ampacity. Substituting the values, voltage drop equals 76 amps times 100 feet divided by the quantity 13.31 square millimeters times 95 amps per square millimeter, which equals 0.61 volts. The ratio of the voltage drop to the maximum allowable voltage drop is 0.61 volts divided by 7.6 volts, which is 5% of 155 volts, resulting in 0.8. Therefore, the number 2 copper conductors are also sufficient for full load current. The provided calculations appear to be accurate based on the information given. However, it is crucial to consult the National Electrical Code, known as NEC, and local electrical codes for specific requirements and to ensure compliance with all applicable regulations. Firstly, conductor sizing is a critical aspect of electrical installations, especially for motors, due to the high inrush currents experienced during starting. The initial calculation uses the starting current of 155 amps. This is higher than the full load current and rated current, and is appropriate for voltage drop calculations during motor startup. The formula used is a simplification and assumes certain factors. The actual voltage drop can vary depending on the specific conductor characteristics, installation methods, and other factors. Secondly, the calculation for voltage drop involves the conductor distance, which is given as 100 feet. This value represents the one-way distance from the power source to the motor. The total circuit length, which includes the return path, would be twice this value. For more accurate voltage drop calculations, especially for longer distances, it's important to use the total circuit length. Thirdly, the cross-sectional area of the number 2 copper conductor is given as 13.31 square millimeters, and its ampacity is stated as 95 amps per square millimeter. The ampacity of a conductor is the maximum amount of current it can carry continuously without exceeding its temperature rating. The NEC provides tables specifying ampacities for different conductor types, sizes, and insulation types under various conditions. It is important to consult these tables, such as those found in NEC Table 310.15, to determine the appropriate ampacity for the conductor being used in the specific application. Fourthly, the maximum allowable voltage drop is specified as 10% during starting and 5% during full load operation. These values are often recommended to ensure proper motor performance and prevent issues such as reduced torque, overheating, and premature failure. The NEC recommends limiting voltage drop to 5% for feeders and branch circuits combined. The calculated voltage drop ratios of 0.8 both during starting and full load indicate that the voltage drop is within the allowable limits for the given conductor size and distance. Fifthly, the overcurrent protection calculation uses a factor of 125% of the starting current. This factor is intended to protect the motor from overload and short-circuit conditions. The NEC specifies different overcurrent protection requirements for motors depending on their type, size, and application. The calculated overcurrent protection value of 193.75 amps suggests a need for an overcurrent protection device rated at or below this value. However, the recommendation to use a 155 amp overcurrent protection device seems contradictory. The NEC allows for the next highest standard overcurrent device rating if the calculated value does not correspond to a standard size. It is essential to carefully review the NEC requirements for motor overcurrent protection to ensure compliance. Sixthly, the NEC provides detailed guidelines for selecting overcurrent protection devices for motors, including fuses and circuit breakers. The type of overcurrent protection device can affect the allowable size and characteristics. For example, inverse time circuit breakers, which trip faster at higher currents, may be sized differently than fuses. Additionally, the NEC requires that motor circuits have both short-circuit protection and overload protection. Short-circuit protection is intended to protect against high fault currents, while overload protection is intended to protect against smaller overcurrents that can occur due to motor overloading. Seventhly, the motor in question is a 3-phase 208 volts, 15 horsepower motor. These specifications are important for determining the appropriate conductor size, overcurrent protection, and other circuit components. The voltage rating of the motor must match the available supply voltage, and the horsepower rating is used to determine the motor's full load current. The NEC provides tables such as NEC Table 430.250 that lists the full load currents for motors of different horsepower ratings and voltage ratings. The full load current is used as a basis for calculating conductor ampacity and overcurrent protection. Eighthly, the calculations provided do not take into account any derating factors that may be required due to ambient temperature, conductor bundling, or other conditions. The NEC requires that conductor ampacities be derated when conductors are installed in environments with high ambient temperatures or when multiple conductors are bundled together in a conduit or cable. These derating factors can significantly reduce the allowable ampacity of a conductor, and it is important to consider them when sizing conductors for motor circuits. Ninthly, the type of conductor used can also affect its ampacity. Conductors with different insulation types have different temperature ratings, which in turn affect their ampacity. The NEC specifies the allowable temperature ratings for different conductor insulation types, and it is important to select a conductor with an appropriate temperature rating for the application. For example, conductors with higher temperature ratings, such as THHN or XHHW, can carry more current than conductors with low temperature ratings, such as TW. Tenthly, the installation method used for the conductors can also affect their ampacity. The NEC specifies different ampacity values for conductors installed in different ways, such as in free air, in conduit, or in cable trays. The installation method affects the ability of the conductors to dissipate heat, which in turn affects their ampacity. It is important to select an installation method that allows the conductors to operate within their temperature ratings. 11thly, the calculations provided do not address the issue of motor starting methods. Motors can be started using various methods, such as across-the-line starting, reduced voltage starting, or variable frequency drives. The starting method used can affect the inrush current and the voltage drop experienced during starting. Reduced voltage starting methods, such as autotransformer starting or part winding starting, can reduce the inrush current and voltage drop, which may allow for smaller conductor sizes and overcurrent protection devices. 12thly, the calculations provided do not address the issue of harmonic currents. Motors, especially those controlled by variable frequency drives can generate harmonic currents that can distort the voltage waveform and cause overheating of conductors and equipment. The NEC requires that harmonic currents be taken into account when sizing conductors and equipment for motor circuits. Harmonic filters or reactors may be necessary to reduce harmonic currents to acceptable levels. 13thly, the calculations provided do not address the issue of grounding. The NEC requires that motor circuits be properly grounded to protect against electrical shock hazards. Grounding conductors must be sized according to the NEC and must be properly connected to the motor frame and the electrical service. It is also important to ensure that the grounding system is effective in providing a low impedance path for fault currents. 14thly, the calculations provided do not address the issue of disconnecting means. The NEC requires that motor circuits have a disconnecting means that can be used to energize the motor for maintenance or repair. The disconnecting means must be readily accessible and must be rated for the motor voltage and current. It is also important to ensure that the disconnecting means is properly labeled to indicate its function. 15thly, the calculations provided do not address the issue of control wiring. Motor circuits typically include control wiring for starting, stopping, and protecting the motor. The control wiring must be sized according to the NEC and must be protected by overcurrent devices. It is also important to ensure that the control wiring is properly labeled and that it is separated from power conductors. 16thly, the calculations provided do not address the issue of surge protection. Motors can be susceptible to damage from voltage surges caused by lightning or switching transients. Surge protection devices may be necessary to protect motors from these surges. Surge protection devices should be installed according to the manufacturer's instructions and should be properly grounded. 17thly, the calculations provided do not address the issue of power factor correction. Motors, especially induction motors, can have a low power factor, which means that they draw more current than necessary to perform the required work. Power factor correction capacitors can be used to improve the power factor and reduce the current drawn by the motor. Power factor correction can also reduce voltage drop and improve the overall efficiency of the electrical system. 18thly, the calculations provided do not address the issue of motor efficiency. Motors have different efficiency ratings, which indicate how much of the electrical power they consume is converted into useful work. High-efficiency motors can save energy and reduce operating costs. The NEC encourages the use of high-efficiency motors. 19thly, the calculations provided do not address the issue of motor maintenance. Motors require regular maintenance to ensure that they operate properly and to prevent breakdowns. Motor maintenance should include inspections, lubrication, and cleaning. It is also important to monitor motor performance and to address any issues promptly. 20thly, the calculations provided do not address the issue of motor replacement. Motors eventually wear out and need to be replaced. When replacing a motor, it is important to select a motor that is the same size, voltage, and horsepower as the original motor. It is also important to ensure that the replacement motor is compatible with the existing electrical system. In summary, while the calculations provided offer a starting point for sizing conductors and overcurrent protection for the elevator motor, it is essential to consult the NEC and local electrical codes for specific requirements and to ensure compliance with all applicable regulations. It is also important to consider all of the factors discussed above, such as directing factors, conductor type, installation method, motor starting method, harmonic currents, grounding, disconnecting means, control wiring, surge protection, power factor correction, motor efficiency, motor maintenance, and motor replacement to ensure safe and reliable electrical installation.